one of the things people have started looking elsewhere from Enig is because nickel is what is causing signal integrity loss or insertion loss, what they call in the high frequency application.
Hello, everybody, and welcome to the Altium OnTrack podcast. I am your host, Zach Peterson, and I'm very happy to be interviewing Kunal Shah, president of liloTree. Kunal is someone who I have seen out there in some other podcasts, and liloTree is a very interesting company, and I thought it would be very great to talk to him on the podcast today. Kunal, thank you so much for joining us.
Zach, thanks for having me. This is always exciting. I think when you describe the symbiosis between the designer and the manufacturing concept, it's always a great bridge for better products, I believe.
I agree, and for myself, I kind of made it my mission over the last year to try and talk more to people who are involved in manufacturing so I can learn all of those little nuances. I mean, I think we rely so heavily on just the design rules to ensure that we don't screw something up or make something that can't be manufacturable, but we can't rely on that. I think you do need to know some of those nuances.
Yeah, one of the things we always harp upon is, as we are going into a next generation technology with the RF and the high frequencies and everything, a lot of times, everything looks great on paper, but when you actually manufacture it, you don't get that performance or the reliability or what you expect. And what it turns out to be is understanding the type of material that need to be included or used to be manufacturing in the manufacturing process is sort of very critical. So if the designer know that, okay, I need to be aware of these things, sort of everything becomes much smoother to what you get, once everything is manufactured from the design perspective all the way to the final manufacturing.
Yeah, I totally agree. Maybe before we jump into that a bit deeper, you can tell us what liloTree does and how you got involved in the electronics industry and how maybe you got involved a little more on the manufacturing side.
Absolutely. So again, I start off with liloTree. liloTree is a innovative sort of a company which actually uses innovation in materials development, especially in the electronic industry. And our main focus or main sort of set of products that we offer in the market is the surface finishes. And not getting too much details about all the products and everything, in nutshell, basically the surface finishes are usually the conventional surface finishes you see or have seen are usually their goal was to just protect copper, by any means. And then it's the solder materials responsibility to form a strong solder joints and realize the reliability. However, the unique aspect of the products that liloTree has developed is actually the surface finishes that actually creates a symbiosis with solder to form a very robust solder joints. So it's actually participating in forming a robust solder joint, so ensuring a better and robust reliability of this electronic assembly. So that is the main difference. But we do have special products for RF, microwave, high frequency that has been very popular in the market. We call it as nickel-less Enig premium. That is specifically designed for high frequency applications. That is running anywhere from 2-3 gigahertz all the way to 100 plus gigahertz. So that is, yeah. But again, coming back to my personal background, again, I'm president and the founder of the company. But prior to that, I again did my PhD in material science and engineering. So that's the developing material is my background. I worked for Intel Corporation as a senior research scientist, developed interlayer dielectric material, which is a low dielectric constant polymer material to realize or reduce the dielectric losses that you see at high frequencies, and then moved on to start liloTree along the way, and we work with a lot of medical electronics, aviation, aerospace, semiconductor, consumer electronics, but and also we receive support from federal government, National Science Foundation to develop these products and commercialize these products for better reliability. Our solutions are eco-friendly. We have gotten rid of cyanide, which is one of the most toxic chemical that is present in gold solution. So our solutions are eco-friendly and enhance reliability and offer better performance in terms of signal integrity. So that's in nutshell me and liloTree.
So when you say a surface finish, there, I don't, I think most designers who are not chemists or have not done anything with maybe electrochemistry may not know how you actually get the finish onto the copper. I mean,
Yeah,
I've done some electrochemistry, but it was metal oxides. It was not,
yeah,
metal surface finishes.
right.
Can you maybe describe the process and then where
Yeah.
the liloTree material fits in? Is it just a solution?
So basically, so surface finishes are, as the designers know that there are bare copper plating happens, and there are different ways of including copper in the printed circuit board. So I'm not going there, but once you have these bare copper pads, right, before it goes into assembly, right, these copper is very sort of instantaneously get corroded, and that surface has to be protected, and that hence the name surface finish is basically you have to include these plating solution on top of copper, and that is what the surface finishes role is, to protect copper, right. Traditionally there have been several surface finishes in the market, back in the day, the immersion tin, where you just put tin, a material which is like, so basically, and then the solder is also mainly tin nowadays, especially with lead free solder. It used to be leaded solder, but now it's a lead free solder. So like attracts like, so it used to solder much better. But however, with the RoHS compliance with lead gotten rid of from these chemistries, the popularity of these lead based immersion tin has gone down. Also, there is a lot of surface planarity issues and a lot of other corrosion based dendrites issues and stuff like that. That has, the popularity of these surface finishes have gone down. The another one that came about almost couple of decades ago is the Enig, electroless nickel immersion gold, where you put nickel layer on top of copper and then put immersion gold, that is a gold layer on top, very thin gold layer, almost 2 micro inches or 50 nanometer of gold layer on top of nickel. It's been the most prevalent surface finish across the world. You will see Enig everywhere, right? The only concern that people have started looking the alternative. It has its own reliability issues, but that's not sort of a limiting factor. People are still using it. However, one of the things people have started looking elsewhere from Enig is because nickel is what is causing signal integrity loss or insertion loss, what they call in the high frequency application. So something that people have started looking, I need to be looking for a nickel free surface finish, because otherwise I'm getting a lot of insertion loss, or I have I'm getting my signal integrity compromised. So that's when the nickel-free surface finishes have started becoming more popular. But along the way, there are immersion silver, OSP, Enipig. So Enipig involves a palladium in the Enig, electroless nickel, electroless palladium, immersion gold. There is immersion silver in the market. There is OSP, that is organic-based surface finish in the market. So every surface finish has its own pros and cons, and I believe that designers should sort of slightly understand what are the pros and cons, and what are the selection criteria for my application, from a signal integrity perspective, and also what is the application, like what sort of an environment, what what is the end application of these devices, because it does affect the choice of surface finish affects the overall performance in terms of signal integrity and overall reliability in terms of the application of these products.
I'm going to be honest with you. When I first did when I first started manufacturing anything, with PCBs, I would go on to the quote form from the manufacturer, and immersion tin was the default choice. So in my first boards, I just kind of went with that.
Yeah.
And then later I realized, oh, most people are using Enig. I should probably do that too.
I,
And and so
yeah,
then I
yeah,
just started going with that.
yeah,
And it wasn't
yeah,
until you brought up some of the issues with nickel-less
yeah,
finishes for
yes,
particular applications that I realized, okay, on this particular design, it's going to be better to go with something that is nickel-less.
yeah.
Is it correct that the issue with nickel is the rough interface that it creates between the outer surface metallic and then the copper, or is there some other issue on top of that with the nickel-less that or with the nickel based platings that creates
Yeah.
problems in these more advanced designs?
Yeah, so in terms of high frequency and the advanced design, as you said, the frequencies are going nowadays, as you are more aware, from almost 2.4 gigahertz into 2.5 gigahertz into 5G to millimeter wave to RF and microwave into 100 plus gigahertz. So what happens is with the nickel, there are sort of two issues with nickel. One is the conductivity of nickel is almost one fourth the conductivity of copper. Now, for example, like from a designer perspective, what do you expect that okay, signal integrity or insertion loss will be bare minimum would be the loss that copper would entail. So copper will always have its own signal or insertion loss, right? You do not want a surface finish adding to this loss, and that is why this surface finish is adding to this loss is called lossy surface finish. You do not want a surface finish that is adding what you are already encountering from the copper, right? So from a surface finish perspective or the design perspective, you should be selecting a surface finish which is a non-lossy surface finish, right? With nickel, instead of the signal passing through copper, now the signal is passing through nickel, and the conductivity of nickel is now one fourth the conductivity of copper. So right there you already have insertion loss because signal is not passing as quickly as it would have passed from copper. And second is also it's a ferromagnetic material, so it does create this electromagnetic interferences at high frequencies. So it actually adds even more insertion loss. And a lot of times people are saying, oh, use thicker instead of thicker nickel, use thinner nickel. But again, you are still living with these insertion losses, and also with the signal integrity engineering, you also at particular frequency you have a skin depth, meaning at what depth these signals are passing. So if you sort of try to engineer that, oh, I'll try to make sure that it only passes through copper and not nickel, or some of nickel and some copper, it becomes very, very complicated. So instead, everybody is now looking for, or all right, instead of going through this complication, let me just look for nickel-free surface finishes. And there are some alternatives out there, and so that actually makes a designer, the manufacturer, as well as the assembly houses, as well as the final OEM's life much easier, because there is no nickel involved, so I don't have to live with these insertion losses associated with it.
So in terms of the nickel-less options available, and maybe you can tell me kind of how liloTree operates in this area.
Yeah.
Are those options only limited to, I think, the immersion based, like immersion tin, immersion silver, OSP, or is there's something else that's probably better, like maybe hard gold? And then like, what does liloTree do within those different areas? Are you licensing a solution? Are you licensing just a process? I'm kind of curious on that.
Yeah, no, absolutely. So to answer your first question, so there are other alternative out there. Immersion tin does have higher insertion loss, so it may not be the best nickel-free option. Immersion silver is a very viable option. It does have a very good signal integrity performance because the silver conductivity is slightly higher than copper. So with everything said and done, the insertion loss performance is very, very much similar to copper. So it's a good performance. However, there are a lot of reliability issues with immersion silver. One being it gets tarnished, doesn't have a long shelf life, also does create a lot of corrosion. Not a lot of, but yeah, it does create corrosion with the sulfur-based environment. So if it's out there in the out there in the open, in the environmental effects would kick in, and it will have a corrosion issues on silver surfaces, and also multiple reflow is a concern. So that is from a silver perspective. OSP also does provide, it's an organic organic base in surface finish. It does provide good signal integrity, but again, similar to immersion silver, it has a low shelf life issues, the reliability issues. It gets sort of exposed, and then the copper would be oxidized, and also multiple reflow is an issue with OSP as well. So even though as a designer, you have to look at signal integrity and the reliability sort of go hand in hand, because if you sort of take care of the signal integrity, if the reliability is not handled, then the overall assembly will have its own issues. So you have to look at like a whole package, that I have to look at the signal integrity aspect along with the reliability aspect. I'll just add one more thing. When I harp on shelf life, because of the nowadays, with all geopolitical issues and everything going on, the supply chain logistic has become so difficult that you have your boards getting manufactured in one part of the world, and then assembly happening in another part of the world, and then maybe the OEM is in a completely different part of the world. And understanding when these manufacturing and then the life cycle of these manufacturing occur, not understanding the shelf life, may put you in a very difficult situation, because we have a customer where they got the board manufacturer manufactured few months ago, and they are almost reaching to a shelf life by the time they are going to do assembly. So they have to go through a lot of testing, that hey, can I even use these boards before I do the assembly. So some of these issues also keep coming back. So the signal integrity along with the reliability sort of go hand in hand. Coming back to hard gold, yes, it's a very viable option. A lot of people just dump absolutely high thick gold onto these copper pads and realize a very good signal integrity. There is a minor issue with reliability, because if you have a very thick gold and if you try to solder those components of those pads, there is an issue of gold embrittlement. So gold gets dissolved into solder, but if there is too much gold, it creates the solder embrittlement, and there is there is a reliability issues and failures along the way. Having said that, a lot of people, if they are not soldering, they just dump a lot of very high thick gold and realize a good signal integrity. The only concern I have, not I, but even the industry has, and a lot of manufacturing supply chain has, is you're talking about hard gold is almost a couple of microns of gold. Like if you think about your PCB of 18 by 24, and you have 50%, 60% coverage of copper, and you're putting 1 or 2 micron of gold, the gold pricing is almost what last time I checked, and that is our raw material, is close to $60 a gram. It becomes it costs several multi-fold compared to the actual PCB without gold. It costs significantly higher, right? Absolutely higher. So that is where liloTree comes into picture. That we have our product that we have specifically designed from a signal integrity perspective, reliability perspective, and cost effectiveness perspective. First, the product is called nickel-less Enig Premium. So basically, what we have is we put a barrier layer treatment on top of copper. That is an organic treatment that we do to passivate copper, so copper does not diffuse through the top layer. And then we only push 50 nanometer instead of multi-micron in hard gold. Only 50 nanometer, which is only 2 micro inches, which is equivalent to the Enig gold that people are aware of. That in Enig, the standard calls for 1.5 to 2 micro inches of gold, and that is the amount of gold we put in on top of this barrier layer treated copper surface. So now the gold is very minimal, only 35 to 50 nanometer, and the barrier layer also doesn't cost much because it's organic based solution. So with a very cost effective solution, your now signal integrity, the signal will most likely pass through copper instead of even gold. It may actually get into gold when you have 100 plus gigahertz frequency. But even if it gets into gold, so signal gets into gold or copper, you are still getting the best signal integrity performance. But the cost is actually in most cases cheaper than Enig. So we have actually brought down the cost even cheaper than Enig, the best signal integrity you can think of, because it's absolutely overlapping copper. So even 100 plus gigahertz, you will have signal integrity performance as good as copper insertion loss, which is completely non-lossy surface finish. But the most important part is, again, with the gold outer layer, you have shelf life more than 12 months. And these barrier layer treatment that I mentioned actually participate in the solder joint formation and forms very, very robust solder joint. So you will not have a solder joint failure. Usually it's used to be a weak link, that usually the failure happens at the solder joint. With nickel-less Enig premium, that has become a strong link. Failure will happen somewhere else, but never in solder joint. And you have the solder material and the PCB materials are so strong. Overall reliability has increased tremendously because the joints have increased. I mean, rather, the strength of the joint has increased tremendously as well. So that is why you have the reliability aspect, you have the signal integrity aspect, and then the cost aspect all covered with our product nickel-less Enig premium. And that's why it's been sort of becoming very popular in the market with everything, every aspect covered of the manufacturing.
Yeah, you mentioned the popularity in the market, and that was something I wanted to follow up on. What does the adoption look like? What has the market response been?
So market response has been is good. The adoption is sort of again, it's organic, but it's sort of coming from the need perspective. So it's like there are a lot of RF and microwave based manufacturers are reaching out to us and adopting our product one by one. We do have adoption in US, but quite a lot of adoption internationally, from likes of Europe, Australia, Asia, that is Taiwan, and China. So again, organically we are sort of getting picked up based on the need, because all those folks are doing RF and microwave and high frequency manufacturing, and based on the need, they reach out and they start adopting. A lot of time what happens is we work with a lot of these OEMs. They do a lot of testing, they conduct in-house testing, make sure it works, and then they sort of reach out to their PCB manufacturer that, hey, they specify nickel-less Enig premium in their design, and then the PCB manufacturer reach out to us and adopt our product. So it's purely an organic based, sort of a need based adoption, than anything else. So which is always satisfying for the fact that, hey, we are supplying something that is needed in the market, and then basically growing from there.
So you mentioned the usage in like microwave RF.
Yeah.
Is that the ideal usage setting, or is there maybe another class of design where it's really applicable, or do you see this growing to be used in every assembly?
Yes. So to answer,
I mean, I'm sure you'd love to have it used in every assembly.
Absolutely, but there is a reason also. There is a tech. I mean, one is my wish list, and second is a technical reason. Then I'll explain. But yes, so RF microwave is sort of a early pickers, because that is out of the need. But a lot of time now, in the 5G high band. So a lot of time you may not see much difference in terms of insertion loss at 2.5 gigahertz. But as you go into 5G high bands, into millimeter waves around 27.5, 25, 27.5, around 25 to 35 gigahertz, you see a significant difference of what type of surface finish used. So now the industry is going towards these technologies. The people have started realizing, oh, I need to be aware of what surface finish I use. So that's where some of these newer customer for us have started sort of reaching out to us and now started adopting that way. But also, if you know that all the automotive industry run around 77, 78 gigahertz. So that is also a big market in terms of high frequency. And then, as we know, with aerospace, aviation, the RF microwave, anything around close to 100, even 100 plus gigahertz is sort of an ideal market. But sort of coming back to your question is, oh, do I like all assembly should be using? Answer is yes, because again, one is my preference and wish list personally, but technically speaking, one is, so Enig is the most widely used, and don't get me wrong, we also sell our own version of Enig, and we are very proud of it. But typical Enig has its own issue with the black pads between nickel and gold. There are a lot of corrosion issues that are always has been prevalent in the market. Then the second thing is also the intermetallics form is between nickel and tin, which is always weaker and brittle compared to a copper tin intermetallic, even without using our barrier layer. Now we are adding our reliability even more with copper tin intermetallics with our barrier layer to even stronger intermetallics. But with the standard Enig, the solder joint is always brittle, right? And even the process of using nickel is also very cumbersome. It's almost requires a babysitting of nickel bath. There are a lot of issues with the nickel plating, and the bath. You may have an overplating and the skip plating in the PCB pads, and they have to X out and throw out those boards, and these are very expensive boards. And just because there is an overplating or underplating or rather a skip plating, you have to X out. Now, one of the things you guys as a designer community, you guys might be doing HDI, where the line spacing is into 5 micron, 10 micron, 15 micron. If you have overplating, you are actually touching from one pad to another and creating a bridge. So it's actually very detrimental to electrical performance. You cannot have these lines touching to each other. And if you do nickel plating, there is a chance of overplating, and these things happen at a micron scale. So it goes into plating, so there is nothing you can control. It just happens and comes out, and you just have to X out because there is an overplating happening. So as we go into these newer generation technologies, the failure is not an option, and these failures happen at a micron scale level. So why do you have to go through all this trouble to plate nickel, where there is an alternative out there which is cheaper in cost and provides you better performance and better reliability? And that's why we suggest that the nickel-less Enig premium process is such that it can actually eliminate the need for nickel in the long run, or even in the short run, with most of these high reliability and HDI and high frequency applications.
So you mentioned something just a moment ago about the intermetallics between copper and tin, I believe, being stronger with the presence of a barrier layer.
Yes.
I'm not a materials scientist at the level anywhere close to where you are. I try to, like I said, I've done metal oxides, but not metals. So I was wondering why the presence of a barrier layer would have any effect on it, because it is an organic barrier layer, as I recall you saying.
Yeah, no, absolutely. So typically I'll explain you what is a conventional case and then what barrier layer does and how it improves it. So typically, usually what happens that when you have the solder or reflow process, how the intermetallics are formed is basically copper diffuses into tin. And then as that diffusion of in the another material which is tin, that coexisting between copper and tin is called intermetallics. But usually in the scenario, like if you do multiple reflow, the copper keeps on diffusing. Also, as the life of these devices, like if you test it at 2 years, 5 years, 10 years, this copper always keeps on diffusing. There is no stoppage of this diffusion. So and basically this intermetallics becomes thicker and thicker. It starts off with a sub-micron into multi-micron thick intermetallics. Now usually whenever you have the strength evaluated, intermetallics is always weak because it's a dissimilar material come together. Those phases have to actually gel much better compared to a homogeneous material, which is a single material. Like if you are talking about tin material by itself or a SAC 305, it's a much stronger than the intermetallics because there are dissimilar material together, right? Now thicker the intermetallics, more chances of failure of less strong material than a thinner intermetallics, right? So the idea of the barrier layer, it's actually at the treatment level, it actually forms this organic solution, forms organometallic compounds, and not only at the surface, but it actually within the copper grain boundary, it seeps through, diffuses through almost 400-500 nanometer of copper surface and completely passivates the top layer of this copper surface. Now what happens that when the soldering process gets on, this diffusion of the copper is actually prevented by this organic metallic compound. So that it prevented to a point, it's not completely stopped, but instead of diffusing multi-micron, it diffuses only 1 or 2 micron. So usually this diffusion sort of delaying process because of this barrier layer treatment makes this intermetallic thickness almost half or 1/3 the thickness compared to a traditional intermetallic thickness. So by reducing this thickness, the robustness has gone multifold.
So, well, it sounds like the main mechanism, just to maybe summarize all this, but the main mechanism is that the barrier layer allows this formation of these organometallics or the organic-based intermetallics
Right.
that then just have a higher or a lower diffusion coefficient.
Exactly.
And so it's more difficult, yeah. And so it's more difficult for this, or it just takes longer, I guess, for this.
It takes longer
this
for
layer
it to
grow over
diffuse.
time.
Exactly, and that makes the
Yeah.
intermetallics thickness very small, and that overall the reliability increases, because every time people measure, okay, what is the intermetallics thickness at day 0 and what is intermetallics thickness 5 years from now, 10 years from now, and you will see multifold increase in these thicknesses. But what barrier layer is able to do is it's actually reduce it by drastically. So what you see after 10 years, you may see what you see after 10 years in a traditional ones, you may, or what you see in 1 year in traditional one, you may see it after 10 years or 15 years. So that the reduction in the diffusion of this copper is what is the key with the barrier layer treatment.
I see. Okay. So this is interesting because it seems to me that given enough time and the growth of these interlayer or these intermetallic layers, eventually it's possible, I guess you could say, that one of these products might fail due to the growth of that intermetallic
Right.
layer in a standard plating process. With yours, you're just essentially extending that time.
Absolutely, and that extension it could be orders of magnitude delaying. So
I
what
see.
you would see it in several years, like 10 years, 15 years, or rather what you see it in 1 year getting really worse. This will take several years, 10, 15, 30 years, 40 years, and because the reduction is drastically reduced, and that, like what I see it, if I give you a comparison. We and our customer did a long-term study in terms of what happens to these intermetallics. So after 1,000 hours of aging, which is almost, some of these are sort of done such a harshly to simulate the 10-year lifetime, 15-year lifetime, right? So after 1,000 hours aging at 150 degrees Celsius, the traditional copper tin intermetallic grew by 10 micron, 12 micron. And the barrier layer treated intermetallic grew by 2 or 3 micron. So almost 1/3 the size of these traditional intermetallics. So you can see it's an order of magnitude slower growth of these intermetallics, and that makes the overall the solder joint robustness significantly higher.
Yeah, that was the next place I was going, was what exactly happens in the solder joint. So it sounds like you're just delaying
Yeah.
natural embrittlement of that solder joint.
Absolutely. So basically you are trying to reduce the phase, which is the intermetallics, as small as possible, because that is the weakest link. You'll always have a dissimilar material that provides the failure. Like if you look at an example of a welding, always the failure happens at the welding site instead of actual metal component. So wherever there is a dissimilar material joining and forming the joint, that's always the small. So, or that's always the weakest. So our goal is to keep it as small as possible so that it doesn't get exposed as much with the stressful environment, and does not create a failure in that phase itself.
I see. Okay, so I mean that's great to understand, and I'm kind of wondering now, why didn't anyone else think of this sooner? Was there just not enough of a market for the products that might need this to even motivate people to do these kinds of investigations?
I think one of the things is if you look at the electronics failure, that industry, like if you look at track the electronics failure in the industry, and from a scientific perspective, number of paper published, in the electronic industry. So most or the majority of failures come from solder joint failures, right? So that has been sort of something that people have been doing. Have been looking into it for decades to how to improve reliability of solder joints. from a different perspective. All right, can I have a different solder chemistry? Can I do this? Can I do this? And people have tried to sort of address it from a different different perspective to see how can I improve the solder joint reliability. And I think we came upon, just because our material science background, and we realized, all right, it can be brought better. We sort of having some inkling that, hey, how can we reduce this size, a copper diffusion, and improve the solder joint reliability. And this is the idea came about, and then we executed it and sort of perfected it, and now it's in the market. But Lord, it's not, we are not the first one who are trying to make solder joint reliability better. A lot of people have done it in a different ways. I believe one of the things is it's easy to use and easy to realize in a mass market based product, and not specific to the application of the area. So you can use this process for all PCBs and realize. So one of the things we do it is we can actually also improve the reliability of Enig, and we call it as Enig Premium, where this barrier layer, slightly different chemistry of barrier layer, is applied on top of nickel to improve the nickel tin intermetallics, right? So we do that there also to improve sort of a standard Enig 2 and Enig Premium and realize the better reliability. So this is the idea of, and this is our way of sort of contribution in terms of how we can improve the reliability of overall electronic assembly. And then sort of adding into it is the nickel-less Enig Premium, not only improving the reliability but also realize the nickel-free option and realize the signal integrity performance, which is being optimum for these products.
I see what you're saying here. It's everyone was looking at just the solder and not where the solder is actually going, which is the plating material.
The plating material, exactly. So a lot of people is like, oh, it's a solder. If you look at the solder companies and if you talk to them, they will always say, hey, this solder material we have come up with, or this a popular solder material has the best solder joint reliability because the chemistry has this and that, and makes it much more stronger joints and stuff like that. So it's always a solder manufacturer's responsibility how to make it better. I think we are the only ones from a surface finish perspective that how can we sort of create a good symbiosis with good solder material and with good surface plating to create this bridge or joint or make this intermetallics much more stronger.
Yeah, it's interesting because if you're talking about solder joint failure and trying to improve reliability through solder chemistries, of course it's going to fall on the solder manufacturers to focus on that. And so I think for them, they're stuck working within the parameters that are given to them, at least at the industrial level, which is what are the surface platings out there. And just by approaching it from a different direction of looking at the plating itself, you can then take that next step towards increasing reliability.
Absolutely. That's very well put, yeah.
Great. This is really interesting. And but you mentioned one other thing earlier, which was multiple reflow issues with some of the traditional surface platings that are used, like an RF. So, for example, immersion silver. So when you say multiple reflow, how do you overcome that issue? I mean, is this just a design challenge to where you need to now, if you are going to use, let's say, immersion silver, you need to design everything so that you don't have to go through multiple reflow? Is there something else that can be done on the back end to improve the reliability of that assembly once it passes through reflow? Or is this really just a matter of, you got to go for an alternative plating material?
I think you may have to just so depends again. So a lot of time, as you know, as a designer, you have double-sided boards, right? So once the reflow is happening on one side, the other side, the surface finish is getting compromised. Like for example, immersion silver, seeing a temperature of 265 degrees Celsius for a lead-free profile, will get tarnished, or OSP will get compromised, because in organic layer, at 100 degrees, 120 degrees Celsius, this material starts to get compromised. So now this is 265 degrees Celsius. Some of these OSP materials will get compromised. It may not see the life of OSP after 2 reflow cycles or 3 reflow cycles. So they are completely compromised per se. So, I mean, again, you could actually look at the design to try to eliminate. So you can actually reduce the number of reflow cycle. But if the complexity of board is such that a designer cannot get away with these options, then you have to look for an alternative, because yes, you are using these surface finishes for a signal integrity perspective, but if it's not manufacturable, or if it creates a lot of manufacturing issues in terms of solderability, because if it's compromised, the incoming solder will not solder well, it will not wet well, and you may have pockets, and a lot of time you may not see some of those things. It may just appear fine from outside, under the optical microscope of some sort. However, there may be a pockets of areas which are not wet well, so you already have a compromised joint in the field. So compromised solder joints that gets into the field, because it's a finished product now. So lot of these things have to be thought through beforehand, and then as you said, you have to look at the alternative option, where you have to look at which alternative will let me do 3 reflow cycle, 4 reflow cycle. We have tested as high as 6 reflow cycle, and it doesn't get compromised because it's a gold based surface. So we do not see any issue with that. And also the underneath barrier layer also passivates copper. So even in any excursion of this reflow cycle, it does not get compromised. 6 plus reflow cycle. And even harsher environments and temperature, the barrier layer has made the copper underneath way more robust in terms of corrosion resistance, and then you have gold layer on top of it. So it's sort of a multi-layer of support in terms of what environment can throw at, and still it can hold up just fine, and it will the solder wet well completely and form a very strong solder joint. So yeah, I mean, the OSP and immersion silver is something that needs to be looked at in terms of reliability. There is another alternative out there which is very seldomly used, but people have started talking about, which is called immersion silver, immersion gold. So they put immersion gold on top of immersion silver. Not very many manufacturers have that plating option, but it's still out there in principle. However, it is also another thing is then you have a 8 micro inches of silver and then additional 8 micro inches of gold. So again, you are adding more and more these precious metal on top of it. Try to sort of try to solve one problem and add another problem of cost and complexity and everything on top of it. With our, in comparison to our process, is absolutely simple. Any PCB manufacturer can use it because it's just barrier layer treatment for 30 minutes at 50 degrees Celsius. The failure is not an option because it's a very forgiving process, and then you just put for 5 minutes for 50 nanometer or 2 micro inches of gold, and the process is done. Versus any alternative process, you have to go through multiple processes. There is a EPIG and EPAG. I'll just add more names, which are nickel free options, which is electroless palladium, immersion gold or autocatalytic gold. These processes are very cumbersome. Like you have to go through some of the catalyst to put in copper on top of, put in palladium on top of copper, then go through the palladium process, and again the palladium bath. It can go. It can be unstable, and you have to babysit it and whatnot. And then you have to go through immersion gold or autocatalytic gold and everything. So it's a very, very cumbersome process and very expensive. Like palladium, as you can see, these days the pricing, with the geopolitical issues, it's almost 1.5 times the cost of gold. So it's even 1.5 times more costly than gold, and you are still putting 200, 300 nanometer of palladium and another 200, 300 nanometer of gold. You're just adding these precious metal to realize these performance, but it just makes very, very expensive. So everybody has to sort of look at the performance, the reliability, and then the cost. So yeah.
Well, I think it's great that you are working towards expanding adoption of a product that tries to balance all of those areas, because I think sometimes as designers we get focused in one of those areas like cost or reliability, and kind of the rest of it goes out the window.
Yeah.
So it's great to hear that there's an option out there that it helps balance that.
Yeah.
If someone were to explore incorporating your product into their assembly, how do they go about doing that?
Multiple ways they can do it. They can actually contact us directly. Be it OEM, the assembly, or the PCB manufacturers. We do have our prototype lab where we can actually apply our technology. They can evaluate, test it out, how much, however they would like to, and then sort of qualify the process. Second option is the PCB manufacturer from OEM or assemblies feedback. Once they specify on their design, they can actually contact us, and we can ship the solutions, and they can set up in their plating lines. So again, this process does not require any capital expenditure. They can use the existing plating line, swap out the solution, put in these new solution, and start using it right away. So that is second option. Third option, lot of even these early adopters have also done, is lot of times that I'm not seeing that our PC manufacturing is adopting it yet. They want to adopt it, but they are still taking time. But we want this product right away because of all the benefits that's been described. So we have a plating line in house as well. So they actually send us the production boards with the bare copper. We apply our technology and then ship it back to the either assembly or the OEM folks, and then they ship it to assembly house, and then they create an entire final assembly. So multiple ways they can realize the benefit of this technology by either having PCB manufacturer adopting, or they can ship the production board to us. We can apply the technology and ship it back. So either ways, we can have this technology ready for them.
That's great to hear. So we're starting to run up against our time window, but what I would like to do is direct any listeners to the show notes. They can find a link to your company website in the show notes, and I think that would probably be a good way to learn about the product and then also get in contact with you guys.
Absolutely. And anybody has any further question, because this is, there's so much information out there that may not be there on the website, that they can always reach out to us and we can provide additional information, maybe testing results and lot many more information that is available to us.
That sounds great. Well, once again, we encourage anyone that's interested to go check out the show notes, and make sure that you go check out liloTree.com. I believe that's the company email or web address.
Yes.
So go check out lilotree.com to learn more about this product. And of course, you can find some information there for incorporating it into your assembly. Kunal, thank you so much for joining me. Like I said earlier, I've seen you out there. I haven't had a chance to talk to you yet, but this has been a great chat. And it's been a pleasure having you on.
Absolutely, Zach. It's been great discussing with you. Thank you. Thanks for having us.
Absolutely. Thank you. And to everyone that's listening out there, make sure that you subscribe to the channel. You'll get updated on all the new videos and, of course, new podcast episodes as they come out. And I think, last but not least, don't stop learning, stay on track, and we will see you next time, everybody.